Today we're going to talk about calculating atomic weight and determining the abundance of different isotopes of a specific atom. On a previous video, you learned about isotopes. You learned that isotopes are atoms of the same element with different numbers of neutrons. Today we're going to talk about what that means in terms of atomic weight and average atomic mass. So atomic weight, also known as average atomic mass, is the weighted average of all the different isotopes of a given atom. We're going to look at the abundance, how prevalent a specific isotope happens to be, and we're going to compare that with the isotope specific mass. If we sum all of those values together, we end up getting the average atomic weight. So it looks like this. This is a formula that you're going to need to know. Average atomic mass, or AW, atomic weight, equals mass times abundance, mass of the isotope 1 times the abundance of the same isotope, plus mass of isotope 2 times abundance of isotope 2, etc., for however many isotopes there happens to be of that specific atom. So you do need to know this formula. Now let's see what that formula looks like in practice. So here's an example where we're going to take the formula we just talked about. I'm going to write that down. The atomic weight is equal to mass times abundance of isotope 1 plus mass times abundance of isotope 2. And if we sum those two values together, we're going to end up getting the atomic weight. Now, we have two different isotopes of copper, which is why I only listed this mass times abundance 2 times. If we had 5 isotopes of an atom, we would have to write M times A 5 times. Now, to keep ourselves organized, I'm going to label this column as the abundances because they're percentages. It's telling me how much of the whole different types of copper would happen to be copper 63 and copper 65. And then atomic mass unit would be M for mass. Now, to set up this math, I'm just going to do atomic weight equals mass times abundance. So 62.9 times the abundance. But the abundance right now is in a percentage. We multiplied by 100 to turn it into a percentage. We're going to want to turn that percentage into a decimal. So that means drop the percentage and move the decimal 2 spots to the left. So 62.9 times 0.6917. And then I'm going to add to that the 64.9 for copper 65 times, change your percent to a decimal, 0.383. 0.3083. If I do that math, I'm just multiplying, then adding, multiplying together. Don't forget about thinking of sig figs and algebra rules. This portion of the problem gives me 43.507. And then this portion of the problem gives me 20.009. Now, because this mass has 3 sig figs and this mass has 3 sig figs, really, these both go out to the 10th position. Now, since we're doing the adding rule, I need to be thinking about my final position being in the 10th position for my final answer. So adding these two values together, 63.516. There's my 10th position, so that means that this problem rounds to 63.5. And then the mass unit is going to be whatever's provided to you, and that is AMU. Now, if you examine this mass to the mass of copper on the periodic table, you're going to find that that calculated mass is quite similar to our periodic table. Specifically, if we look, copper has a value of 63.55. We can do a different type of problem as well. Instead of solving for the atomic weight, we can also solve for the abundance of a specific isotope. Now, this problem happens to be a little bit more difficult because we're going to have to use a little bit more difficult algebra. Instead of solving for AW, we're going to know AW. It's going to be provided to you in the problem, or you're going to find that number off your periodic table. Staying organized, just like in the previous problem, is very key for doing this. When we solve for abundance, you have to remember that all percentages need to add up to 100%. So if we happen to have 60% abundance of isotope A, we would have to have 40% abundance of isotope B. And since percentage is really just a decimal times 100, all decimals need to add up to 1, and that's how we're going to set up our algebra. So we're going to take 1 minus the known abundance that happens to be provided in the problem, and then we're going to set that equal to the unknown abundance. And that's going to look like a problem like this. So here we're going to do a problem with rubidium, and we're going to actually solve for the abundance this time. In this case, we're provided the 2 isotopes of rubidium, and it's important that it's only 2. We can't solve for more than 2 in our class. We're going to have rubidium 85. So you can see I'm starting out by staying organized, and I'm going to write down its mass. So here's my mass column, which is 84.9118. And then I'm going to continue reading, and I see that I also have rubidium 87. That's provided to me in the problem, and its mass is 86.9002. Now we're also going to have an abundance because we're going to use the same formula that we used before. Atomic weight is equal to mass times abundance plus mass times abundance. The atomic weight, it's told to us as an atomic mass, but that's the same as the atomic weight. So AW in this case happens to be 85.47. If you weren't provided with this 85.47, you would look it up on your periodic table and you would use the average atomic mass at the bottom of your periodic table square. Now, abundance has to add up to 100%, or if you're just talking about numbers, it's going to add up to the number 1. Your 2 decimals will add up to number 1. So if this happens to be abundance A, a number we don't know yet, the remainder of the abundance is 1 minus this value, what that ever happens to be. So then when I set up my actual equation, I plug numbers in. I'm going to take my atomic weight, the 85.47. I'm going to set that equal to the mass of my first isotope times its abundance, 84.9118 times A. I'm going to add to that the mass of my second isotope, rubidium 87, 86.9002 times 1 minus A. Notice this is all in parentheses because this is one value. That's the abundance. It's the whole term here, 1 minus A. Then we need to distribute some numbers through. 86.902 needs to distribute through both portions of these parentheses. So to rewrite this all, 85.47 equals 84.9118A plus 86 times 1, of course, is the same value. And then times a negative A means 86.9002A is negative. At this point, you want to start to combine like terms and move some variables around. So I need to start by moving this term that's not connected to A to the other side because that's my side without A. Since this is plus, I need to do minus. And if I do it on one side, I have to do it on the other. So these cross off, and I'm left with a negative value, negative 1.4392. And that's going to be equal to these two put together. So I have a positive 84.911A, and then I have a negative 86.9002A, which results in a number something like this. Negative 1.9974A. Now to solve for A, I need to remove my coefficient by dividing since it's being multiplied. I need to do that to both sides of my equation. So these cross off, and then I'm going to be left with A. A is going to be equal to 0.72053, and that is this value right here. So that's my abundance right here for rubidium 85. But this is as a decimal, so I would need to multiply it by 100. I'm just going back to some sig fig stuff. What I let you do on these ones, because we have the addition subtraction rules all happening with multiplication and division also. I just say let's use the smallest number of sig figs. In that case, it's this one provided to us. So let's call it 4 sig figs, and that would put us to right here at the 5, which would give us a percentage abundance, move the decimal 2 spots right, 72.05%, and that is for rubidium 85. So now I need to do 100 minus 72, which would give me 27.95% rubidium 87. We want to box that answer so we can find it. Make sure on this problem, especially if it's asking for the abundance of each isotope, that you're providing both isotopes and you're labeling which one is for which.